I'll turn it over to Ed. Ed's going to lead the session. He's going to introduce our next speaker, and then we're going to literally take off.
Thank you very much. Well, we cannot literally take off, of course, unless we have propulsion. And that's what our next speaker here is here to talk to us about. XCor Aerospace is the company which is building the Lynx spacecraft right now down in Mojave. They've been working on it. They had hoped originally to fly early this year. Of course, nothing ever happens on schedule in aviation, as we all know. But we're very confident that we will see the Lynx flying in a few months from now. And about a year after that, if all goes well, it'll be in commercial service. And we're all very excited about this. We're also very excited about Virgin Galactic and all the other great companies that are in this new industry. And on that note, I'll introduce you to Kathy Rodway from XCor.
Thank you, Ed. Hi, everyone. I'm just going to boot up the computer here. Yeah, it was just okay. There we go. We got sound. That's a good sound. We might have to turn it down because rocket engines are kind of loud. All right. Now, let's make sure this works. Does it? No.
We didn't focus on that.
Okay.
So this is yours.
That'd be great. Yeah, because I'll stand over here because I want you all to look at the slides, not so much at me. I'm just well, we can't start at the end. We got to start at the beginning. There we go. You got it?
Yeah, so this is the down button goes to the next slide.
That's good. Great. All right. Hey, how are you? My name is Kathy Rodway. I am Director of Payload Sales and Operations at XCor Aerospace. I'm going to tell you about XCor, give you a briefing in case you don't know who we are, what we do. I'm going to tell you about what we're doing, i.e. the Lynx. I'm going to give you a development update, tell you where we are with that, because I know you want to know. And stand up, Nadir. I have a colleague here, Nadir.
If you have technical questions, come to
Nadir's a senior design engineer, or design engineer, one of those half and half kind of things. But he is helping to build the vehicle. I've got Brian Campen in the back, who's our director of media and public relations. And non-technical, or the marketing. That's it, right? That's the three of us here. So I'm going to tell you who we are, what we're doing with Lynx, why we're doing it, and how we're doing it. Some of the experiments that we've got going on. This is my grocery list because I always need one, even though I have it in the back of my head. All right. No, that's not going to work. Okay, who we are. XCor has been around since 1999. We're in Mojave, California, which is about an hour and a half northeast of LA, past Edwards Air Force Base, at the Mojave Air and Spaceport, the first inland spaceport in the whole country, despite what Spaceport America says. California has it over New Mexico. We design, build, and test engines, vehicles, components, and materials. We've got 14 different rocket engines designed, built, and tested. We've had over 4,000 engine firings since 1999. We are building Lynx, and as if you didn't notice by what Ed said, yes, that's coming. I'll show you that in a minute. What we do, rocket engines. We started by building small rocket engines. We did something called the T-card engine, which was a 15-pound thrust nitrous oxide alcohol engine that we took to conferences, we took to state fairs, we took to schools. We got some of our first investors by firing this rocket engine in the hotel ballroom in Scottsdale, Arizona. No joke. Ed talks about citizen space, citizen scientist. That's how we are. We're founded by not a billionaire with deep pockets, but 4 very hardworking, dedicated people who wanted to go to space and wanted to take everyone else with them. That's why we're doing this. So we built a small engine, just to see what would happen, to show that a private company could build a rocket engine. And then we did the same with a rocket plane. This is a Long Easy that was owned by our chief engineer. He essentially donated it to the company. We took the piston engine out and put 2 400-pound LOX, liquid oxygen, and alcohol engines in there, just to see what would happen, just to show that a private company, not the government, could build a rocket plane. We had no idea what was going to happen. We got Dick Rutan as our first pilot. Dick, as I think most of you know, Dick is the first person to fly nonstop around the world. He was the first pilot on this. He just, I think his comment was, it was a kick in the pants. We wound up flying it 26 times and breaking a world record. Then we started building bigger engines. We got a NASA contract here. This is a liquid oxygen methane engine, 7,500-pound thrust. Again, built that just to show, well, we were some of the first ones to have a LOX methane engine. And then we built a second rocket plane. This is a Velocity airframe, again, an existing airframe that was built. It was built for a company called Rocket Racing League. They wanted to do something called NASCAR in the sky. They wanted a 10-minute turnaround, like, very short pit stops like you have in NASCAR. And they wanted a LOX kerosene engine this time that had a very bright plume so that everyone can see. And we've taken this engine, we've taken a lot of the technology, lessons learned from this engine, and applied it to our next engine. This is the Lynx engine. So here, this is one of the engine firings that we had. That's probably the long duration one that we did. And I'll show you a video of that in a minute. So we'll have 4 of these engines. So imagine this times 4. So Lynx. Lynx is a suborbital reusable launch vehicle, SRLV, as it's known. It's pilot +1. So that +1 can be a person, it can be a payload. Horizontal takeoff, horizontal landing. Takes off on a runway under its own power. That runway can be 7,500 feet as a minimum with the appropriate airspace. So doesn't mean Moffett Field, doesn't mean SFO or LAX. It means a FAA licensed spaceport. Where are we with this? We're in development. Here's a lot of the components that you can see, some of the major structural elements. Here's the cockpit pressure vessel. It will be pressure vessel, although you will still be wearing a pressure suit. And here is the fuselage, which contains the LOX tank. Wing strakes here. This is the propulsion system. It's on, there you built this, the truss system. I talk about this all the time. This is great because we can take the entire propulsion system off of the fuselage and work on the propulsion system separately and then put it back onto the fuselage. All of our test stands are on wings, actually, are on wings, on wheels. And here you'll see this. This is a video for the 67-second engine firing that we've done. So you see us, we're towing it out of the hangar. You have the fuselage, you have the propulsion system. Guys are doing final check, LOX loading. And again, this is liquid oxygen and kerosene. Things that you can spill on the floor and clean up with kitty litter.
Second engine run in 10, 9, chill, prime. Good. 6, 5, 4, 3, 2, arm.
And away we go. seconds. This is the longest duration engine run that we've had to date. We will be having longer duration, about 3 minutes. We haven't done that yet because just last week we got the full-scale LOX tank installed in the fuselage. And for us, that never gets old. So we also have, we'll have 12 reaction control systems or thrusters. They will be, if you see images of our vehicle, you'll see dots on the image. Actually, I have a brand new bag that has a Lynx image on it, and I keep thinking I had dirt on it, but no, it was actually the dots for the RCS that was there on my bag. We have fired this. We've been working on this for the last couple of years. This is sort of our go-to engine. This is something that we have. We're very happy with. It has become, that T-card engine I was telling you about. This has become our T-card engine. This has become the engine that when we have VIPs and special visitors, and even just people that we really like in big groups, we get the guys together and say, hey, how about doing an engine firing? 20 minutes later, sometimes even 10, they're firing this engine. It is it's one of the standards that's available that we're just right now just refining. Our avionics, we're really happy with that. We did an engineering cockpit mock-up that we used to basically populate with the avionics and check it. And actually had our pilot is now Rick Searfoss. He's a 3-time space shuttle, twice space shuttle pilot and once commander. So he's flown that. And so he would sit in the cockpit and say, well, I think we need to move this gauge over here and let's put some buttons over here and switches on this side. So he's really been instrumental in helping us figure this out. Our aerodynamics, we've done a lot of wind tunnel tests. We've relied actually more on wind tunnel tests than we have with CFD. But there it is. This is actually from our boss, from Jeff Grayson, and he's the one that wrote that. So if he writes that, I believe him. So it's done. It's looking great. We've added these. Nadir, what do you call these?
Fences.
Fences. Okay, we've added the fences. That's a new thing from some of the wind tunnel tests that we've done. So here they are. They're loading the full-scale LOX tank into the fuselage, and in parallel, what we've got going is that fuselage, but we're also building another fuselage, so that what we can do and what we'll be doing in the next few months, we'll probably have this. This is the fuselage being done in North Carolina, North South Carolina, one of those company called Blue Force. This is going to be the flight fuselage. This fuselage here we're going to be using for our propulsion system testing. So in parallel to building the airframe, we can continue with the propulsion testing. Here's a cockpit. This is being done in Atom Works in Colorado. Here's Rick Searfoss being suited up. This is Orbital Outfitters is doing our pressure suit. So he's sitting in the engineering mock-up, literally being fit checked. Here's the wing strakes. This is where we are with these. We'll have these. All these major elements will come within the next 2-3 months. And once we have these big parts, then we'll start putting the airframe together. But like I said, at the same time, we'll continue to do propulsion tests. I don't suppose we did any propulsion tests this week. We'll probably do some this coming week or next week. I don't know. I was out of the office all week, so who knows how. We're probably far advanced from when I left. Landing gear, we've tested our landing gear. We've tested actually to even more load than what we really need. We're really happy with this. You did some of this, didn't you? This a little bit on this? Yeah. So, yeah, drop test. So you can kind of see, I mean, I think you guys are on the same wavelength as we are. As I said, we don't have a lot of money. We don't have a lot of resources. We don't have large government contracts or a billionaire with deep pockets. We make things work with the resources that we had. We have. So here's our forklift with this apparatus that we built, welded, designed, built, put this together to accommodate these load tests on the landing gear. And we're just outside of our hangar here in Mojave. So where are we? Well, we've got the wing vendor. We've changed wing vendor. We've had a phase 1 with the company, and didn't quite work out the way we liked, but we know what our wings are going to look like. We know what that design is, so we just need someone to build it. Our nose design, we're working on that. Engine cowling needs to go on. We need to do a closed loop thermodynamic cycle on the propulsion system. Propulsion system, by the way, is propelled by piston pumps. This is something where we got a DARPA contract back in, starting 2000, 2001, where we started to build a breadboard piston pump because turbo pumps were A, too expensive, and B, really unreliable for a reusable vehicle like ours. What we want to do with Lynx is literally bring it down, fill it up, and go again. We intend to do that 4 times a day. So we started building this piston pump and have now flown a fuel pump, 3-cylinder fuel pump, on the X-Racer. That test that I showed you was pump fed both with LOX and with fuel. And again, a 3-cylinder piston pump, very much like you have in your car. And again, it makes for the reusability, it makes for low cost, it makes for all of these things that we say that we can do, these high tempo operations, come back down, fly again in 2 hours, call it up in 2 hours. So all the stuff that makes it a commercial vehicle. We need to do the test with the flight LOX tank that I showed you, and then assemble the main vehicle core, plumb and wire that main vehicle core, and then start our flight test operations. We'll start our flight test operations probably third, fourth quarter this year. Flight test operations for us means taxi tests, runway hops, then we go up a little bit, come back down, go up a little higher. We have wings, we are aircraft-like operations. We can do that. That's why we're doing it. Yeah, do you remember this? I mean, when I was growing up, this is where we're supposed to be right now. And guess what, we're not. And, thank you, Ed, for saying, how much it takes citizen scientists to do this, because it is taking us to do this. But we're doing it because there's lots of stuff to do. Space-based solar power, it's huge. NASA has it as a major line item in their budget. They're going to really be taking a look at this. It's a new form of energy. Communications, right? Where would you be without your satellite, your cell phone, your GPS? I mean, GPS, you'd be totally lost. Direct TV, people do not realize what would happen if we did not have the satellite communications. The day would end. Actually, I know some people I work with, the day would just be totally lost. Biotech, life sciences, lots to be doing up there. Microgravity, Ed's astrobiology challenge, that's just the tip of the iceberg. You talk to people who are already doing this, or already thinking about this, new drugs, just new way of thinking about pharmaceuticals, for example, nanotech. It's all out there. A settlement. We're doing. I mean, it's going to happen. May not happen in my lifetime, but we're going to get up there. We have to get up there. There's 9 billion people on this planet, and it's not getting any smaller. I mean, the population of the people. The Earth isn't getting any bigger. But I know somebody's going to be talking about this, I think later today. Mining materials, basically space access. That's what we're talking about. Planetary sciences. Lots to look at up there. And I'll show you an example of a group that is doing that on links. Atmospheric sciences. Jason Ryman was going to be talking about noctilucent clouds. They call this area between the mesosphere, lower thermosphere, atmospheric scientists and aeronomists, they call this the ignorosphere. Because they're either looking at it from the ground-based observations, or they've got satellites that are, way up here, looking through it. But until now, well, actually, since the X-15 program, we haven't been able to get in situ measurements. Right now, we've got a lot of models. Jason will tell you all about noctilucent clouds and the gases and CO2 and methane and all that stuff that's up in there that we don't know about. We can, like I said, we can model it, but not a lot's there. So then Earth observation. This is the Springs fire. If you've been listening to the news lately, this is what's going on down in Ventura County. Just point of reference, I used to live about, I think it's down in here in the cloud zone. This is, see if I can get it right, it's MODIS. It's a NASA satellite. Moderate resolution imaging spectroradiometer. This was taken at 11:15 a.m. by NASA's Terra satellite, 11:15 a.m. on May 2nd, on Thursday, soon after the fire broke out. What you see here, these red images, is what MODIS has picked up as an area of extreme and intense heat. So you can kind of see an outline of what that zone is. Imagine going up. So actually, let me just back up a minute. What happened was Terra satellite took this MODIS image at 11:15. There was another image at 2:30 by the Aqua satellite, again with MODIS, that again shows more dots, basically more area of where this fire is. Imagine going up 4 times a day and monitoring a fire like this. It's already burned, somebody help me out, like 48 square miles. I think it's a huge fire, 20% contained. They think it's going to be contained somewhere around May 13th, 9-10 days from now. It's a huge fire. Imagine going up and monitoring this thing 4 times a day and really helping the firefighters out. Okay, so how are we doing this? This is our development plan. Right now we're working on Mark 1. Mark 1 is the prototype. And Mark 1 has these capabilities. It'll get you to 60 kilometers at apogee. Goes about almost Mach 2.5. Mark 2 is a production model. Mark 2 will get you to Mach 3 on the descent, Mach 3.5 rather, and 100 kilometers in altitude. Mark 3 is a variation, a derivative of the Mark 2 that has a pod on top. And here's what I'm talking about. This can hold a max mass of 650 kilograms. Basically a small satellite, a 10 kilogram satellite, or an instrument. I think Ed talked about this. You've got 2 spaces back here, call them cowling, payload C, payload C, port and starboard. It'll hold about a 2U CubeSat. And then on the interior, you have the right seat. Remember, Pilot Plus One. And we can take the right seat out and put something like a 19-inch rack in there. We can also put payload A, which is this regular shape back here that holds about a 20 kilogram max. And I'll show you some of the stuff that we can do in there. Losing my voice. Okay, so here's a profile of Mark II. I think this stuff is out there on the table. So you can see what's known as the CONOPS, concept of operations. Take off from a runway, horizontal, go up. You're going up at almost Mach 3. Engine cut off at 3 minutes. You get up less than 5 minutes, you're going to be at apogee. You're going to be up at 100 kilometers. That's almost 330,000 feet. And then you come back down. You got a max G-force at 4 Gs, and then engines are off. Up here, it's only the reaction control system and so on. So engines are off. You're going to do a glide landing and land back at where you took off. So here's something that we've already talked about. This is, yes, made in Texas. We can't emphasize that enough. XCor right now is in Mojave, California. However, we are moving to Midland, Texas. Most likely sometime before the end of this year is up. So this is what Ed is doing. Ed talked about this. Here's something that comes out of the NASA Flight Opportunities Program. This is being worked on by Todd Smith at Johns Hopkins Applied Physics Lab, and basically he wants to. It's a simple. You can kind of see this. It's a very simple electromagnetic, commercial off the shelf electromagnetic mill and field mill and magnetometer sensors. And what he's going to do is measure the EM both inside the vehicle and just outside in the vicinity of the vehicle. Again, here's something that comes out of a Flight Opportunities Program contract, although this group in Indiana called TechShot has been building this for quite some time. This is for life sciences experiments in microgravity. This hardware has the ability to change fluids in cultures of living cells under the microscope. And actually this was that, being able to change fluids in the cultures of living cells was something, under the microscope, was something that was initiated by Charles Lindbergh. So you can kind of see, you've got sort of 2 capillary tanks in here, and this is where the fluid gets piped through. You've got a microscope/camera here, and the electronics here. This is the size of a briefcase. So again, this will go payload A behind the right seat. And here's the Mark III, launching a small satellite, launching 10 kilogram satellite. I talked about planetary science. This is Planetary Sciences Institute is developing this suborbital observatory. This is basically a very high resolution telescope that they're going to put into links on top in the I'm sorry, I can't go to the grocery store without this. Yeah. So this is something that they're putting up into the dorsal pod. Why? Well, because they like the frequency of our flights. They like the ability, or the fact that we can go up. They can call us up in 2 hours, and we can go up if they need to see something, some transit that's going on. I think Jason will talk a little bit about that. They've already done an on-site design and fit check, so they've learned a lot in terms of payload accommodations. So that engineering mock-up that I showed you, they've done that. So they like the frequent, flexible flights that Lynx gives them. And then here's just an image of a satellite launch that I think you all have seen. But instead of me sort of telling you about how Lynx is going to fly and everything, I'm just going to get the experts to tell you. And then you can get a sense for yourself.
The experience is something I am personally looking forward to. Like all of the things that I experienced flying the shuttle, all of those phases of flight are there. Boost, the weightlessness, the fact that you're up in a pilot seat as opposed to being in the back like a passenger of an airliner. This is more like the right stuff kind of experience. The person who gets a ride on board the Lynx will sit side by side, slightly aft from the pilot. There'll be 2 sets of controls. We'll be wearing pressure suits to fly it.
It's about a minute after engine light to go supersonic.
We anticipate about a 75-degree flight path climb angle that we'll use in our trajectory.
Going faster and faster and steeper.
We're going straight up. That's the key element of it. Things happen in a hurry. That altimeter's clicking by pretty darn fast.
70 to 80,000 feet, the sky starts to turn dark. By 100,000 feet, it's not black.
So once we get to main engine cutoff, we'll have a brief period of weightlessness, and the arms will kind of float.
And then you have several minutes to enjoy the view and enjoy for yourself the sensation of being where so you would have gone before.
Let's get an opportunity to maneuver using the reaction control systems, turn it upside down and pick different attitudes and just hold there. You're going to get a spectacular view. Be able to see out to the Grand Canyon, all the way down Baja, California, looking out, seeing the sun glint on the Pacific Ocean, and then from there it's just a long glide back home. But looking at the Earth from space, it's virtually life-changing. Really the key driver to what will make this experience so special.
So that's it. I'll be around all day, so if you guys. If you have any questions, just come see me. And unless we're taking questions now, Sean.
Yeah, sure.
Yeah, sure. If we have time. Yeah, right here.
On the glide back in, I can't help but notice the similarity to the space shuttle in terms of glide back in. What about the heat underneath?
Yeah, we've thought of that, but we're not coming in at Mach 25 like the shuttle did. We have, if you look, let's see, we can go back to the image. We've got a thermal protection system on the vehicle. It's what did I just do? If you look here at the leading edge and underneath on the nose, that's a thermal protection system that we've been working on, and so yeah, we've accommodated that. It's not tiles. In fact, it's so secret I don't know what it is. Nadir might, but I don't think he can tell you.
We're going back at Mach 5, so heat load is much lower than on space shuttle.
Yeah.
We'll be all right.
Kathy, you mentioned that you need a 7,500 foot runway and you need a spaceport. Is that longer than a commercial runway? I don't know what a commercial runway is.
Well, I mean, I know the longest runway, for example, at LAX is like 11,000 feet. So in other words, it's not 7,500 feet is not a whole lot, basically. And so we could do it. The point is we could basically do it almost anywhere with the appropriate airspace.
So that's what you mean by needing a spaceport is more the airspace.
Yes, the appropriate airspace. An FAA licensed spaceport means that airport, that landing strip, is in a low density population area. It means FAA is very concerned with third party damage. So they don't want something to happen to the vehicle. They don't want an explosion that is next to a housing development, for example. So in Midland, we're looking at Midland. We like Midland. They like us because basically what we're doing is taking off and going over oil derricks. Now, is that safe in case the vehicle lands? Well, FAA doesn't care. We're not gonna hurt anyone. Any third party. So
once your operations are running, what's the lead time between group of young engineers here having an experiment ready, what's the period of time before they have to communicate to you and the flight?
I think I understand your question. We could.
Time to book it. How many months beforehand? You need to book the flight.
I think we're looking at something like a minimum of 90 days to start that process. Yeah, and we'll start taking customers. We'll start taking paying people, whether it's a flight or a participant. Most likely, if all things go well, and we're on track as we are now, most likely in about a year. So kind of end of, say, third quarter of next year.
I have a quick follow-up. In that case, with basically one passenger or your set payload capability that you have, I guess your propulsion system allows for a far greater turnaround of flight times, flight events per vehicle.
Yes. Yeah, we're looking to fly 4 times a day. So we can do a turnaround in under 2 hours. So, you know, and then at the same time, sort of to add to your question, you know, we've got primary and secondary payloads. So you can have a person, it could be somebody that you don't even know, flying in this seat, and then flying, you could fly something behind the pilot's seat.
One more question?
I don't know if I want to. What?
I was just curious, following on the previous question, I was wondering if XCor done calculations yet for runways that are higher than sea level. If there's, say, a terrestrial feature that has a particular interest, you know, say, I don't know, say over Bolivia, where you're 10,000 feet runway, how much runway would you need for operations?
It's a good question. I don't know that we've done that calculation yet.
So that's 7,500 feet at sea level.
Yeah, I don't know. Okay. Thanks, everyone. Thanks for coming out on Saturday, too.